On our discussion of polymer dynamics, and today we're going to talk about polymer diffusion. So thus far we've been talking about basically a scenario where we're dealing with one type of polymer in the melt, so multiple chains, no solvent, and really we've been talking about a single polymer species, i.e. self-diffusion. But what happens if we have a scenario where we have a melt with two different species of polymers, A and B? What if we have two species, and what if the two species are different molecular weight? Or actually, let's say we have a scenario here where we have long polymers and then short polymer chains. And what if here we have a long polymer like this, but then short polymers of our other species? Well, hold your horses with all these questions, and let's think about it from one step at a time. So we're going to think about it from two different scenarios. So the first, fixed obstacles. So let's imagine we have a background matrix of large entangled polymer chains. So, i.e. the large polymer chain, because we know that the larger polymers, higher molecular weight, will be in that entanglement, the reptation regime where your kind of entanglements are permanent, they're topological obstacles, they're constraints that we have to kind of entangle and disentangle. So the shorter polymer chain will diffuse among these topological constraints. So you can imagine I have a large polymer or several large polymers like this. They act as constraints, kind of along here where these entanglements occur. So my shorter polymer is going to have to kind of diffuse among, again, it's a much shorter polymer. Let me undo that. So my short polymer is going to have to travel like this. It's going to have to go through these and basically diffuse, basically move among these topological constraints. So the larger chains will have a much lower diffusivity, obviously because they have these topological obstacles. They're constrained, they're entangled, they're in that reptation regime. So they will be basically, they're going to appear to be fixed compared to these faster moving short chains. So even though they have to move along these obstacles, what you'll find is, actually it depends, we have to kind of make sure that the distance between here, these constraints, so this distance between the constraints is going to be kind of along the order of the size of your polymer or smaller. So if that distance is less than the radius of gyration, actually, let's go this. Let's say the radius of a gyration of our polymer, actually I'm going to grip in blue, that radius of gyration squared is less than that distance between here, this distance between constraints, then that chain's going to be able to move easily through it. But anyways, if you have small chains, again, they're going to diffuse among and between these topological obstacles or these constraints, these entanglements between your larger chains. And thus, your larger chains are going to be, appear to be fixed, and they're going to basically be your rate limiting step. They're going to diffuse very, 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 very slowly. So that's looking at it from this perspective of fixed obstacles. You can also look at it from the perspective of kind of these large polymers as well. So constraint release. So for a large polymer, or long, very, very long polymers, the small chains are going to act like just a featureless background. So they're not going to necessarily entangle as much, and they're not going to have permanent permanent constraints or topological obstacles. So you can kind of think about this scenario of long polymer is going, constraints are going to diffuse. So your long polymer, your basically entanglements are going to fuse against this viscous background without encountering topological obstacles from the shorter chains. So that's kind of a key point. So the short polymers are going to diffuse much, much more quickly than large chains, and any topological constraints, i.e. entanglements, are going to disentangle much, much more quickly than the large chain could interact with them anyways. So in this scenario, you have your large polymer and it's diffusing, and when it runs into kind of these short chains here, they're not going to kind of entangle like they would with a much larger polymer chain like this. So why? Because again, in this short polymer is in the Rouse regime. So that Rouse time, the longest relaxation time, is much, much faster. So even if they kind of, again, touch and entangle, your smaller polymer is going to disentangle so much more quickly than that Rouse, than the large chain, than basically before they can interact with them anyways. So they will not, small chains will not constrain the motion of your large chains. Whereas, again, and similarly for the small chains, again, they're not going to really, they're going to be able to diffuse among these topological constraints, but they're still going to diffuse much faster. So that's kind of the idea here. So that's kind of the best way I can kind of think about it. So for the small chains, there's basically going to be these constraints, again, permanent entanglements from big polymers interacting with other big polymers, and your little polymer here is going to diffuse among them here. For your large polymer, you are just going to be kind of moving, let's say you're diffusing in this direction, and when you encounter a small chain, yeah, they might interact and hit, but they're not going to entangle because why? This small chain is going to disentangle, it'll hit, disentangle, and then move on to the next one. That's kind of the concept here. So their large polymers just move like through this viscous background, whereas your small polymers will move basically among this kind of array of topological obstacles. So in this same kind of argument holds if you have a polydispersed sample as well. So large polymers, much slower diffusion will dominate the overall diffusion process, i.e. they're your rate limiting step. Now, this is going to be, the diffusion of species is going to be very different in the blended case than in your self-diffusion case. So when you have polymers A and B, it's going to be a little bit of a different scenario. And so you could kind of think about that the enthalpic effects are going to play a larger role. So do the species, basically, if they like each other, if they prefer to be mixed, so if there's some strong intermolecular interaction, i.e. if your chi is, let's say your chi is very, very low, or even if it's less than, if your chi is less than 0, then we're in really, really good shape. The diffusion will tend to speed up because, again, they want to mix. So that inter-diffusion essentially is what we're going to be talking about in this scenario. So the chi parameter is going to reflect, again, that enthalpic contribution. Chi is greater than 0. Mixing will not be preferred enthalpically. And because of this enthalpic barrier, interdiffusion will be slowed down quite considerably. And actually, it could be stopped completely. So for immiscible polymer blends. So we know if I'm mixing two polymers here and here, what's my critical chi-in for mixing? Chi-in has to be, if they're the same molecular weight, so if it's equal to 2, hopefully remember, or actually, chi-in is going to be equal to 2. Again, that's your macrophase separation, all the way back to lecture 4, the most important lecture here. So if your chi-in is, again, if your chi-in is less than 2, you're going to be mixed. If it's greater than 2, then you are going to be phase separated. So that's kind of the key idea that we're looking at there. So your critical chi, or your chi-in values there can really kind of change the diffusion process that you're working with in some of these problems. So if you're macrophase separation, again, that critical chi-in, hopefully people remember, again, chi inversely proportional to temperature. So we have our chi-in versus here, we saw kind of this parameter here. So at high values of chi, we're at very, very low temperatures, it's going to want to demix. So for macrophase separation, we saw that this chi-in was equal to 2. So below 2, low chi, not high chi, you're going to want to mix. But basically, if you're above or at equal to 2, you're going to phase separate. So if you're 50-50 mix. However, when chi is less than 0 and you prefer to mix enthalpically, so if your chi is greater than 2, so if it's greater than or equal to 2 for 50-50, your interdiffusion is going to be 0. If it's, again, if it's still low, if it's less than, if your chi-in is less than 2, if you're somewhere around here, it's going to still slow down compared to your, again, in our homopolymer case, our chi-A, that was equal to 0. So if you're between 2 and 0, it's going to be slow relative to kind of what we've been talking about previously. However, if you're less than 0 and you're preferred to mix enthalpically, you could find essentially this free, you could kind of looking back at lecture 4, the free energy of mixing, you could see we've only kind of discussed this case, but if it's less than 0, our enthalpy is going to dominate, and here, this term is going to dominate kind of our mixing. And you can see this factor of n here. And it's actually, that free energy scales with n. And it's found experimentally that this factor of n, it will increase the rate of diffusion by an additional factor of n. So increasing basically the molecular scaling above, which would, from the previous derivation. So we previously saw, way back over here, Let's look at our viscosity scaling. Let's look at our diffusion scaling. The log of diffusivity was to the -1. So our plot could look like d. So if you see something like this, molecular weight of this and this, where this is -1 and this is 0, then we know that our chi is less than 0. So let's go all the way back here. Oops, to this page. Oops, to this page. So if chi is less than 0, your diffusivity increases by an additional factor of n. So this is kind of like a driven type of motion. Again, a thermodynamically driven type of motion for your polymer coils into each other due to kind of this free energy difference. So an increase in your diffusivity speed. So again, each of the polymers, DA, DB, they're going to want to mix. So that's kind of the key idea here. So if your chi-n, let's just assume again, macrophase separation, polymer here, we're trying to see if they mix. Again, homopolymers, 50-50, or basically 50-50 mix. If your chi-n is greater than or equal to 2, then our diffusion for A or B is going to be essentially, or our interdiffusion essentially into one another is going to be 0. If your chi-n is between 0 and 2, your interdiffusion is going to be kind of less than the diffusion we kind of predict in our Rouse or reptation type of regime, because again, we're dealing with self-diffusion. So here it's equal to 0. So if you're actually greater than 0. But anyways, you get the picture. But if your chi is less than 0, now you get that increase in diffusivity by this factor of n. So next time we're going to go through one more little kind of supplemental discussion of the Rouse and reptation regime, and then we'll get on to mechanics. So, see you.